Okay, so now we are going to cover actually in total 11 questions or 11 exercises related to chapter 11. And as usual, I'm not going over first couple of pages, 2 or 3 pages that have actual questions. I'm repeating a question in full under answers, and so that's what I'm covering. I have already scrolled down to answers. So first one, what type of isomerism is present in each of the following pairs? And so in each case you have pair of compounds, and you're supposed to identify type of isomerism. So isomers have identical molecular formula, but have some differences, some other differences. So depending on the type of difference, nature of difference, then we identify different type of isomerism. So first one, these are actually Regio Isomers because functional group or functional groups are in different positions. So carbon skeletons are identical. In each case, carbon skeleton for both compounds is cyclopentane. What is different is position of hydroxyl and amino group. In first case, it's 1, 2. In second, 1, 3. So those are Regio Isomers. Now, while one on the left is cis and one on the right is trans, they are not stereoisomers. You will see actually that brings us actually to the next example. So they are regioisomers because functional groups are in different positions, 1, 2 versus 1, 3. That makes them regioisomers. Same skeleton, but functional groups in different positions. Now, for them to be stereoisomers, they must have identical structural formula. That means they cannot be regioisomers. So substituents must be 1, 2, like this. So 2-amino alcohol, 2-amino-cyclopentanol, 2-amino-cyclopentanol. The only difference is that one is cis, one on the left, and one on the right is trans. So cis-trans, those are stereoisomers. So those are two stereoisomers. Identical structural formula. You see under A, these structural formulas were not identical. Simply by looking at line formulas and you can see that they are not identical. But here they are. If you didn't indicate with wedge dash stereochemistry of each substituent, they would appear to be completely identical. So they are, in that sense, they have same structural formula, but they have different orientation of substituents in space, and that makes them stereoisomers. And finally, C is probably the easiest, because these two molecules have identical molecular formulas, but they have different functional groups. One has alcohol, the other one ether. So they are functional isomers. And these C also can be classified as skeletal isomers because they have different carbon skeletons. In one case, carbon skeleton is a 5-membered ring. In the other case, it's 5-membered chain that is part of larger 6-membered ring that also includes oxygen. So different skeletons. So in this case, depending on what are the options for C, it may be multiple choice. And so in a multiple choice, you would be looking for something that fits here. It's certainly not regioisomer, certainly not stereoisomer, but functional skeletal isomers would be good. Or if you are writing in answer, then one of those two. So that's question number 1. Question number 2. How many chirality centers are present in the compound below? So you have to be very careful and count those chirality centers properly. So let's start. Okay. So I will start at the left. You can start at either side. At the left, we have a ring. And when there is a ring, there is often confusion among students. What do I do with the ring? Because for carbon atom to be chirality center, first it has to be tetrahedral. So carbon atom with double or triple bond cannot be chirality center. It's not tetrahedral. So it has to be tetrahedral, and it must have 4 different substituents. There are other instances of chirality, but in introductory organic chemistry course, we're not concerned with them. Some maybe a little bit more advanced organic chemistry courses will introduce you to those like chirality of allenes and biphenyls, but we don't cover them, particularly in as accelerated course like this summer course. So really all you need to be concerned with is something like this. So carbon atom with 4 different substituents. And you will be using models on the test, so you may want to make models in advance. Now, depending on the nature of the question, even though a question may be stereochemistry question, you may not need a model. Still, it doesn't hurt to have model prepared before the exam. So you may want to prepare things like tetrahedral carbons or 2 tetrahedral carbons connected to each other, in case you need to examine 2 neighboring. And you may want to prepare pairs. So to have 2 tetrahedral carbons and maybe 2 of these. And also you may want to have a ring, at least 1 ring. Typically 6-membered ring, but maybe 5 and 6. But if you make 6, you just remove 1 carbon and you snap 5-membered ring. That's what you need. Depending how much time you have, but in this case you will have, since you're working at home, you will have enough space, hopefully, for everything. So let's go back. In this case, I wouldn't use a model. Okay, just a minute. I didn't realize that. Okay, at least I can mute one. I cannot mute my own laptop because I do have another monitor, but I cannot mute my laptop because I have to hear you. So if we are suspecting that chirality center may be part of the ring, that carbon still must have 4 different substituents. And so when you're going around the ring, what you're looking for first is any carbon that has 2 different substituents, those that are outside the ring. And so this one labeled with a star, and that's how we actually label chirality center, with a star, carbon star, that's chirality center. It has this whole large group, and proton, hydrogen is not shown. So hydrogen and this group, those are 2 different substituents. And then question is the ring, so that ring part, is that chirality? Do those constitute 2 different substituents? To figure that out, what you do is you start at that chirality center, suspect chirality center, and you draw a line to cut ring exactly into 2 equal halves. So with this carbon that we indicated with asterisk, you cut exactly in 2 halves. That means carbon 4 will be the other end of that line. In case of 5-membered ring, you would actually go through the middle of the bond. So if ring has even number of carbon atoms, that line that cuts ring into half will go through 2 atoms. If ring has odd number of carbon atoms, it will go through atom that is chirality center and middle of the other bond. You may want to practice that, and there are, of course, other exercises like that I already provided for you. Now, when you look at this ring, you can see 2 halves, and now actually the reason why we cut ring into 2 halves is that those are 2 substituents. 2 halves or 2 substituents are not identical. One has double bond, the other one does not. So this is chirality center, because there are 4 different substituents. And then rest is the chain. So let's consider a chain. This carbon has methoxy group, this 6-membered ring. It has hydrogen as 3rd substituent, and this rest 4th. 4 substituents, 4 different substituents. That's also chirality center. And again, next one, amino group. These 2 different groups, obviously different groups, and hydrogen as 4th chirality center. Here, methyl. This one is a neopentyl group. No, it's not neopentyl. So 3, 4. This would be actually isobutyl group. This is isobutyl group. A neopentyl would have one more carbon. Isobutyl group, so methyl, isobutyl, hydrogen, and all this big group. So there are a total of 4 chirality centers. Often students make mistake and include the last one as chirality center. Basically, every substitute carbon to the student is chirality center. But make sure that substituents are not identical. And in this case, it's methyl and methyl. And this is particularly easy to miss because you're looking at the chain and you are kind of looking at chain mentally differently from substituent. And so this is just part of a chain. You're not looking at it as substituent, as methyl group, but actually it's methyl and methyl. And therefore, that's not a chirality center. So there are a total of 4 chirality centers. So practice that. Practice how to identify number of chirality centers in a molecule. Okay, so let me see if there are any questions. Okay, I don't see any questions. Okay, let me see. Well, the student who sent me an email. Okay, that's not something that I can address now. I thought it was something related to the class, lecture. Okay, so let's go back to question number 3. Which of the following compounds is chiral? So when you're given names, some students can figure out which one is chiral. That means which one contains carbon with 4 different substituents. So some students can figure that out from a name. I would advise against it. Spend a little bit of time. Yes, I know time is limited on the exam, but spend a little bit of time and make sure that you got it right. And in particular, because actually when we give you names like this on a test, we want to test, do you know how to convert name into a formula? So it's more than one aspect of the question. And so if you make a mistake in converting this, particularly mentally when you're doing conversion, maybe you know how to do it, but when you're doing it mentally and are trying to imagine what 2,2-dichloropentane looks like, and then is it chiral and make a mistake, well, that's on you. You don't get any points, obviously. So this is A. This is 2,2-dichloropentane. And then this is 3-bromo-1-pentanol, 3-bromo-3-methylpentane, and 4-methyl-1-pentanol. So which one has chirality center? Well, A obviously does not. It does not have any carbon with 4 different substituents. Carbon 2 has 2 identical chlorines, and 3 and 4 are CH2 groups. B, that one has chirality center, right here. Carbon 3, because that one has bromine, hydrogen, not shown, ethyl group, and this group that is CH2, CH2OH. So actually this OH breaks the symmetry. And so it's unsymmetrical compound, and therefore chirality center for different substituents. Double check. C, you see, this one has bromine, methyl, but these are 2 identical ethyl groups. Again, don't assume that chain constitutes 2 different substituents. When you have a substituent on a chain, often students would tend to assume that chain constitutes 2 different substituents. And this is often what students would assume when they try to imagine a formula. Instead of drawing it, try to just figure it out in their head. This would be a common mistake, identifying C as an enantiomer. Another common mistake could be D, not realizing that 4-methyl, that 4 is on carbon next to last, and so last 2 substituents or last 2 groups are methyls, and they're identical. So this is not chirality center. Again, trying to visualize it just mentally without drawing it, it could result in identifying this as chirality center, and obviously it is not chirality center. 2 substituents are identical. So correct answer is B. Just double checking it. Oh, okay. Yeah, chirality center is carbon that has 4 different substituents. Question number 4. Which of the following is a Fisher projection of the molecule shown below? So this is the molecule. Actually, there is a video which surprisingly few students watch because I can see a number of views. It's very easy to convert Fisher projection to perspective drawing and vice versa and so on. So you can do it on paper, or you can make a model. And so maybe you can make a model like this, and then designate each of them. Let's say white is hydrogen. And so hydrogen is projecting towards you. Red is oxygen. So hydrogen is projecting towards you. Red is oxygen. And then you can designate this as ethyl, or even make it, let's say, 2 carbons. And so call it ethyl so that you don't get confused. Ethyl, and we're going to insert it all the way in its pocket here. And then this will be cyclopentyl. And now how do you convert it to Fischer projection? Well, Fischer projection is bow tie convention. So which means you simply flip it in such a way that when you look at it, horizontal bonds project towards you and vertical away from you. And you look which of these formulas matches it. Which of these formulas has OH on the, let me see, on the right, hydrogen on the left, cyclopentyl down. Actually, this is it. If I look at compound A, it would have to have, yeah, OH, H, yeah. So A seems to be all right. Let's see. Actually, no. The problem is that camera is looking one way and I'm looking at formula the other way, and that's so let me see. Let me make sure that I made correct isomer. Okay, so hydrogen. Oh yeah, of course. Since I'm looking at it the opposite way, I made a wrong enantiomer. Okay, so I hope you don't get lost, but that's very difficult when I'm looking at formulas and then this is looking the other way. Okay, so OH up, hydrogen projecting towards you, ethyl to the back, and to your right, my left, and then cyclopentyl. We're using green as cyclopentyl. So let me make sure. Yeah, that's the one. So that's will be if you're making a model. Again, you can just use this formula and manipulate it as I have shown here, or in one of those videos that are on YouTube that I put on YouTube. And so now you look which of these formulas, you know that it's bow tie projection or bow tie convention. So horizontal bonds, and this is OH and H in case of A. Horizontal bonds have to project towards you. And then you look at the other two. And you can see that actually H and OH are flipped, or if you get them correctly, then so H and OH are flipped. If you get them correctly, the H and OH, then ethyl and cyclopentyl are flipped. So A is not correct. B actually appears to be correct. And that's, yeah, this is B. H and OH are projecting correctly towards you. They are on horizontal bonds, that is projecting towards you, and vertical bond on top ethyl and bottom cyclopentyl. So B is correct. And then you can use models, the other models, of course, for C and D, it's cyclopentyl and ethyl that are horizontal, so they have to project towards you. Don't use this. Don't do something like let's see, yeah, like this. This would be wrong. That horizontal bond projects away from you. That would be enantiomer. So make sure that horizontal bond always projects towards you. So the horizontal bond, that's bow tie projection. It has project towards you. If it projects away from you, then you're actually looking at enantiomer. Of course, I'm flipping this molecule. It's the same molecule. It's not enantiomer, but Fischer projection indicates that according to Fischer projection, horizontal bond must project towards you. That's the only way to compare this formula with a Fischer projection represented in 2 dimensions. You may need to do a little bit of practice, but in any case here, it's B. An alternative way would be, if you don't want to do any of it, is simply to determine whether this is R or S. And so determine and you would find that this is R configuration. And then you go for each of these and figure out what is the configuration, R or S. And one that is R, B, is correct. So that's another way to do it. I have a question. How did OH go from being a solid line in the plane to projecting towards you? That's simply a Fisher convention. So here is how we did. So in a perspective drawing, we typically represent two bonds on chirality center in the plane of the drawing, one projecting towards the viewer and one away from the viewer. In Fisher projection, chirality center is the only atom that is in the plane of the drawing. Two substituents project towards the viewer, those are horizontal ones, and two away, and so away from the viewer. So this is how we do the transformation. So we flip the molecule. So you see how we did this flip. We moved this cyclopentyl substituent down. So we take the molecule. So this is cyclopentyl. And if you're dealing with a drawing, we simply move cyclopentyl down like this, so that it's kind of vertically down. And then flip molecule like this, and just move it like that, and that's it. And so that's what we do with on paper with a drawing. That's the procedure, and that's how we went from OH being vertical in the plane of the drawing to being projecting towards you. So this is perspective drawing, this is Fisher, but this is actually what Fisher means. So when we draw this cross for four bonds of Fisher projection, that's what they mean. The two horizontal bonds are projecting towards the viewer and two vertical bonds away. Okay, I hope that answered the question. Question number 5. Provide UPAC name for the molecule shown below. Show your work. No credit will be given for a simple guess. So UPAC name means that if compound has stereochemistry, then you have to indicate stereochemistry like RS. And so, first of all, you have to determine the order of priorities. And so this is the order of priorities. Hopefully by now from chapter 8, you know how to determine order of priorities. Atom with highest atomic number has the highest priority. And then if you have multiple bonds, you may have to convert multiple bonds to virtual single bonds, virtual atoms, and so on. We will deal with that part in the next question. In this case, you don't have multiple bonds. So all that you're doing is determining the order of priorities. So actually, in this case, looks like I made a mistake. So let's see. Just fix it in a minute. Oxygen has higher priority than carbon, of course. It's a little bit difficult to get the correct arrow. Okay, now I'm not able to change color of the arrow. Okay, maybe here. Okay. Okay, so priorities are 1 for oxygen. Then these two carbons have the same priority. We can leave them for later. 4 is hydrogen. So 1 is oxygen, these two carbons, same priority, and hydrogen 4. So next, when we look at atom of next highest priority, to this carbon we have oxygen that is bonded. And here are all hydrogens. Oxygen, higher priority than hydrogen. So as we follow path of highest priority in each of these two substituents, you see that this top carbon has higher priority than bottom, which means that order of priorities is 1, 2, 3, and 4. And now we have to flip them in pairs. And actually, I'm looking just at that. Yeah. So what you do is you need hydrogen on a vertical bond, lowest priority substituent on vertical bond, so that you can determine whether it's R or S. Because if hydrogen is on a vertical bond, or in general, substituent of priority 4 is on vertical bond in Fisher projection, you can ignore it. And you simply look at 3 substituents that are that form 1, 2, 3 array, whether it's clockwise or counterclockwise. And in this case, it's counterclockwise, so that's S. And when you are typing the answer, I made a mistake again. Sorry. What's going on? Let me just retype it. Okay. So this is what showing your work means, because RS would simply could be a guess. And I can't have you simply guessing, also guessing are 50%. So this is what showing your work means. Showing what is the order of priority of substituents. So showing that priority 1 is hydroxyl, priority 2 is this methoxymethyl, and 3 methyl, 4 hydrogen. And so name of the compound is S1-methoxy-2-propanol. 3 carbon longest chain, that's propane. On carbon 2 is hydroxyl group, so that's 2-propanol. And on carbon 1, we have methoxy group, so 1-methoxy-2-propanol. Let me just double check. Yeah, it is S. You can always make a model and determine from a model whether it's R or S. Simply from a model, this is hydrogen, and then you give, let's say, OH, and then 1-methyl methoxy, and then you look at it in such a way that you don't see hydrogen, and whether this is clockwise or counterclockwise, 1, 2, 3 array. Question number 6. According to Kahn-Ingold-Prelog rules, what is the correct way to replace double bond with virtual atoms in these substituents? This is like thioester. So what you would do is you redraw everything, and then double bond, carbon-sulfur double bond, you redraw it as a single bond. And on carbon, where you have a double bond to sulfur, you now draw two single bonds. One is existing single bond, or the first bond to sulfur, and you draw another virtual bond shown in blue. At the other end of that bond is atom that is at the other end of the bonds relative to carbon, that's sulfur. Carbon is bonded to sulfur, so it's another carbon-sulfur bond. So you converted carbon-sulfur double bond to two carbon-sulfur single bonds by adding virtual single bond and virtual sulfur atom. And then for sulfur, you repeat the same procedure. Sulfur forms double bond to carbon. So on sulfur, you draw two single bonds. One is the existing, so it's already there. You only draw the second one. It's shown here in blue. And then at the other end, with respect to sulfur, is carbon atom. So carbon is going to be virtual atom. And so that's correct way to replace this substituent. Okay, let me stop recording here, and then I'm going to make another recording with the rest of this exercise.